Now, the most important, or like one of the most important use of validation is model selection. Now, what does model selection mean? Well, it could mean that whether you're trying to choose between a linear model or a nonlinear model, or whether you want some order polynomial in a model, or what regularization parameter you want, all of that comes under model selection. So let's look at a very generic scenario wherein we have like this data set dn, and of course, because we're using validation, we're going to split it into n minus k, and then here is the validation set. Okay, so this is, as I think we said earlier, but let me reiterate that this is the training set, and sometimes also denoted by the train, and this is the validation set, and this is also denoted by dval. Okay, so what is a model? A model is nothing but like a hypothesis set plus an algorithm, right? So there can be many ways in which these like models differ. So let's assume let's assume we have like these different models, and I'm denoting each of these models by like M1, M2, M3, and so on. Let's say we have M models, so MM, right? And so model selection is that each one of these, so basically I'll have like some, and by the way, like these could be like, let's say M1 has a hypothesis set 1, H1, and so it's a linear model, right? So let's say this is H2, which means let's say it's a neural network, or and so on, right? And so what we do is that we train our model, right, based on whatever data we have. And so in this particular case, what I'm doing is I'm going to use the validation set later on. So I'll have like a validation and a training set. And so based on my training set, which is like the train, essentially, I'm going to train my model. And eventually I'm going to get this final hypothesis. So let's say I get G1 here, G2 here, and G3, and GM. Okay. So, like based on these outcomes, of course, I will be eventually getting eval, which will be the estimation for E out, right? So we already talked about that, E out of G1, and so I'll have E out of G2, G3, and so on. So, like, which one of these should we pick, and what should be the basis of doing this, like picking the final hypotheses? Now, if we are running these models behind closed doors, as we said earlier, we obviously have no idea of what's going on, what each model does, let's say. But the only thing we have is this estimate of E out, right? So how do we answer this problem of which one to pick? And a short answer to that question is using validation. So how is that going to happen? Again, let me reiterate what we did earlier. So I have M1, M2, M3, and so on up to M of M, right? And what I'm going to do is I will use dtrain as we said earlier, right? And if in this case we assume that we are using the entire training like data and somehow evaluating E out, what we are actually intending to do is that we are really using the deficient dtrain. And so that's why I'm going to like write these as the minus ones, right? So G2 minus, G3 minus. I'm just saying that if it wasn't evident in the previous slide. So that's why we'll have this deficient hypothesis. Why? Because we have a validation set using which we will do the validation. And so using the validation set, we're going to calculate errors and then eventually produce the estimate for E out, which is going to be my validation error, but it's going to differ because each one has a different hypothesis. The deficient hypothesis, of course, but each one will have its own. So this is essentially an estimate of E out of G1. And then this one is going to be an estimate of E out of G2 and so on, right? So I'll have like these different error terms as well. So in this case, it's EM, which is again based on GM negative. Okay, so now what I'm going to do is I'm going to pick the model with the best validation error. So basically what I'm trying to do here is that I have all these hypotheses, and then maybe you can think of these as like some finalists in a competition. and I need to pick the final hypotheses from this set, right? This is what's happening here. I have this like set of hypotheses and I'm picking one from there, right? So what does that mean? So basically that means is that I have this new hypothesis set H minus that has all these deficient hypotheses in them. G1 minus, G2 minus, and so on up to Gm minus, right? And so basically, what is this? This is like a finite collection of hypotheses, a finite collection, right? And because we have this like finite collection of hypotheses, which is a hypothesis set, I will pick one based on my validation error or the validation set, right? So let us assume we picked like any one of these. Let's say I picked G3. And so I'm going to denote this by G star because this is the one that I picked finally based on my validation error, right? And so here is the thing, the validation error, eval, right, is going to be like, that is going to be my estimate for E out, right? And in this case, we cannot apply single hypothesis Hofting inequality that we have because we have to pay the price of choice. What is that choice? Because now we are like picking up from, like we have a choice of these different hypotheses and we're picking up one. Earlier, we just had one deficient hypothesis, and so the relationship between E out and E val was way simpler than what we have right now. So now we'll have E out G star negative because obviously that's also deficient one, and that is of course less than equal to eval again G star negative plus a term that is of the order, and this here is log m over k. Now, where does this log like m come from? We have this option of selecting from m hypotheses, right, for finite hypothesis sets. So essentially, what we are getting here is the VC bound for finite hypothesis sets. Let me write it down. Finite hypotheses sets, right? And so because like we have this option of choice, we are like paying the price and we have this like m included, which wasn't the case earlier. Okay, so having said that, now the other thing that like comes to our mind is that we cannot output the G negative that we eventually came up with. Again, going back to the first goal of model selection, the goal of model selection is to select the best model and output the best possible hypotheses, right, from that model. So essentially, we want to select the model, whatever that is, which has E out, which is like minimum when we have all the data there because we don't want to lose any information. So model selection using a validation set relies on the leap of faith that if my E out on the entire G, right, if my E out is like the smallest one, it's the best one, then because this is just like G minus is the best one, and so my G with the entire data will also be the best one. So of course we are making a huge leap of faith there, but practically it turns out to be correct, right? So what we are saying is, let me write it down quickly here, is that my E out of the one that I've selected, right, on the entire data, which is not deficient, so let's say G star is less than equal to, although we are not proving this and we are making this leap of faith, and of course this might not be all the time true, but in most situations it is true. Right, so with the same hypotheses, I'm going to evaluate like, and I will say that this is the estimate of E out because this relationship exists. GM or G star, this is not M, star, and then this is the deficient one plus order square root log of M over K. Okay, so basically what I'm saying is that the star is selected using validation, but then we learn again using all the data and output like this G. We output this G, which like satisfies this entire equation, right? So what we are saying is that, of course, this is a leap of faith because it's not necessarily the case that like the one G star that we are using will produce the best E out of G star, right? Uh, and what happens if this is not the case? So if this is not the case, then maybe our result is going to suffer, but in most practical situations, that is the case. Okay. So having said that, let's move on to the next application, and let's write it down here only. So next application of validation is that we can use a validation set to select the value for the regularization parameter. Remember in the augmented error equation, so we can select that because lambda was a big question in regularization, if you remember. So let's see how we can pick regularization parameter using this principled approach of validation. Okay, so how do we pick this lambda? Again, we look at these hypotheses, for example, H1, H2, and so on. Let's say HM. And just like we did earlier, run the model selection, for example, on D train. Yeah, so first it's, D train, and then pick the deficient hypotheses based on that, validate it. So dval, calculate the error, and let's say I get E1. So similar to that, I'll get E2 and finally EM. The same idea applies. So each of our models will have this. And so, yeah, one thing to notice here is that these H, they are not different. So they are the same hypotheses, but they are considered different models because they have the different regularization parameters. Like maybe a better way of representing this would have been like M1, M2, M3, such that all of the hypothesis sets are, let's say, H, and then the only thing that's changing is my lambda. So for example, lambda 1 was 0 here, and lambda 2 here is 0.001 here. And then finally, lambda m is some, I don't know, some value 0.1. Okay, so how are we going to decide which lambda to use? Well, I'm going to pick the best G, like the deficient hypotheses, which is producing the smallest error, right? So that's how we do the regularization parameter selection using validation. Now, an interesting question is whether we should run G negative or the deficient G negative with the entire data set or not, right? Because again, we've said that like multiple times before that we don't want to output the deficient one, but rather we want to output it with the entire data. But now we have decided which regularization parameter to pick based on that deficient hypothesis. Well, short answer to that question is yes, you can. You might have to make certain adjustments when you run it with the entire. So basically, when you get G and then you still use the same lambda, because let's say this lambda was the best one, right? And then I run it with the entire data, and then maybe this wasn't the best. But then sometimes you have to make adjustment. Again, there is this leap of faith that in most of the situations it is the good one, right? Okay, so what is the key takeaway from all this, like two applications of validation? Remember this big picture, and it can have like many such applications. The big picture is that we have this data, finite data, and we split it into two parts. And based on that, we have this deficient hypothesis, and there are certain trade-offs that are happening, and we need to be aware of them when we are applying it to a certain application. Okay, so finally, let's talk a little bit about the general philosophy of validation before we move on to our another important topic, that's cross-validation. But first, let's talk about the general philosophy. Okay, so we've been after E out all the time, right? So basically, we learned from some data set, which was a deficient data set, and then we got some G, and then we were after E out. And then we denoted it by a G minus. But basically, we wanted to learn G, right? Although we had this deficient hypothesis, that's fine. So we wanted G, and then we somehow created a relationship between G and G minus. And then there was this K, which is the validation set, and the rest of the data, which is the training set, and N minus K. Okay. Now there are these like three relationships that always existed, and we said there is this leap of faith that we are taking when we are saying with the entire data set, this G, which is my hypothesis, is almost like very close or less than equal to E out when calculated with the deficient hypotheses, right? And then this was like really close to eval of G minus plus that error term that was there, right? Of the order, like maybe in most cases it was this, right? Okay, so K plays an important role here. Why? That's because imagine like this K is large, right? And so we want this K to be large if we want this relationship to be tight, right? If K is large, then this relationship is tight because this is what the error bar is, right? So this diminishes, and so we have a tighter relationship. Now, what happens here? What do we want here? Now we have this deficient hypothesis versus like the overall hypothesis, which is based on the entire data set, right? If my K is small, right, so maybe I can say K big. If my K is small, then I'll get a tighter bound here. Why? Because if my K is small, I'm not like putting away a lot of data, and so I have a better relationship between G and G minus. It's not really that deficient. And so we have this like chain of inequalities, and how should we like resolve this trade-off that exists? So the big question here is, can we come up with a K that is like that kind of takes a middle ground and like resolves both the issues? So maybe can we, like that's a question that we're trying to answer. Can we get away with, can we have maybe, can we have K equals 1? Yes or no, right? How can we resolve this K issue? So the answer to that question is yes, we can, and we're going to answer that in the next video when we start talking about something that's known as cross validation.